In the last video, we introduced the proximal gradient method, which is an optimization algorithm which is similar to gradient descent, except it's able to handle an extra non-differentiable term in the objective function, assuming that non-differentiable term is simple enough. This can be useful, for example, if we are training a machine learning model and we're using L1 regularization. That L1 regularization term is not a differentiable function. So the standard gradient descent method can't handle it, can't handle that non-differentiable function. But the proximal gradient method is able to handle that. And at each iteration of the proximal gradient method, we have to evaluate something called the proximal operator of our regularization function R. And the proximal operator was defined like this. Here, R is a function that takes a vector as input and returns a scalar as output. For example, R of beta might be equal to the L1 norm of the vector beta. And what the proximal operator does for us is it takes a vector beta hat as input. This vector beta hat could be any vector in the input space. And the proximal operator solves this little mini optimization problem here. And what's happening here is we are trying to reduce the value of R, but we're penalized for moving too far away from the input vector beta hat. And the ability to solve this optimization problem efficiently is a useful thing to be able to do in an optimization algorithm. And we're going to see in this video how to evaluate this proximal operator explicitly in the special case where R is the L1 norm. So we're going to look at the special case where R of beta is equal to the L1 norm of beta. And to be explicit about the meaning of this L1 norm, suppose that the components of beta are beta naught, beta 1, dot, 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 beta d. These are the components of beta. And then the L1 norm of beta, by definition, is just the sum of the absolute values of the components of beta. So it's equal to the absolute value of beta 0 plus the absolute value of beta 1 plus dot, 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 plus the absolute value of beta d. It's just the sum of the absolute values of the components of beta. That's the L1 norm. We want to compute the proximal operator of this function R. We want to compute the proximal operator of the L1 norm. And by the way, what is this number alpha? This is a positive number. And we mentioned last time, you can think of this number as being like a step size. It controls how severely we're penalized for moving away from the input vector beta hat. If alpha is large, then this term is not weighted very heavily, so we're not penalized very severely for moving away from beta hat. So it's like we have more freedom of movement. We can move further away. And if alpha is small, then this term is weighted heavily. So the price we pay for moving away from beta hat is severe. So we are pretty limited. We have to stay close to beta hat. We can't move too far away from beta hat. So before we compute the prox operator of the L1 norm, as a first step, let's compute the prox operator of the absolute value function. So let lowercase r be the absolute value function. It just takes a scalar beta, a real number beta, as input and returns the absolute value of beta as output. So of course the graph of r just looks like this. It's the absolute value function. And now beta is a scalar in this example. So let's compute the proximal operator of this absolute value function, the proximal operator with parameter alpha. So this proximal operator is going to take a scalar beta hat as input. Beta hat is a scalar now because r is just a function from r to r. And the proximal operator is going to solve this little mini optimization problem we want to minimize the absolute value of beta plus 1 over 2 alpha times beta minus beta hat squared. This is the little mini optimization problem that the proximal operator is going to solve in this case. And so if we want to evaluate the proximal operator of the absolute value function, we have to solve this optimization problem analytically. To do this, I'm going to consider two separate cases, two distinct cases. So case one is going to be the case where beta hat is non-negative. And then I claim that in the case where beta hat is non-negative, I claim that there is no value in allowing beta to be negative. In other words, if beta hat is non-negative, I claim that it's impossible that a negative value of beta will give us a minimizer for this problem. There's no way that a negative value of beta can minimize this objective function if we're assuming that beta hat is non-negative. And let's try to understand why that's true. Here's the number line. Here is 0. Here is beta hat. It's some non-negative number. Suppose that we're considering a candidate value for beta, which is a negative number. Is it possible that this number beta is a minimizer of this objective function here? I claim the answer is no, because if we have a negative value of beta, we can improve this value of beta just by moving to the right a little bit. Suppose that we start here and just move a little bit to the right. The new value of beta that we get is going to be strictly better than the old value of beta. Why is it strictly better? Because certainly this term gets smaller. If you start with this value of beta and then you move to the right a little bit, we're getting closer to the origin. So this term is certainly getting smaller. But also, as we move to the right, this term is getting smaller too, because we're moving closer to beta hat. So there's no way this number beta could be optimal. We can improve it just by moving to the right. And that can, as long as beta is negative, we can always improve it by moving to the right. So there's no way that a negative value of beta can be optimal for minimizing this objective function. So that means that when we're looking for a minimizer for this objective function, we can restrict our attention to positive or non-negative values of beta. But if we're restricting our attention to non-negative values of beta, then this term here simplifies. We can remove the absolute value function. So what we have to solve is now we just have to minimize this function. The absolute value of beta is equal to just beta because we're restricting our attention to non-negative values of beta. And this term remains the same, 1 over 2 alpha times beta minus beta hat squared. And we're restricting our attention to non-negative values of beta. But this is a nice simplification. Being able to replace the absolute value of beta with just beta, that's a nice simplification, because this is just a quadratic function of beta. And we know how to minimize quadratic functions even from pre-calculus. We know how to minimize quadratic functions. The graph of this function of beta, its graph looks like a parabola that opens upwards. And we know how to find the vertex of that parabola from pre-calculus or from calculus. How do we minimize a function in calculus? Well, we just set the derivative equal to 0. So minimizing this function with respect to beta should be pretty easy. Now there is a little complication, which is that we're restricting our attention to non-negative values of beta. And so there's two possibilities here. Here's possibility one, is that the vertex of this parabola falls to the right of the y-axis. So the possibility one is that if you graph this parabola, then the vertex falls to the right of the y-axis. And in this case, the value of beta that we're looking for is just the value of beta right here. It's the same as the value of beta that minimizes this quadratic function. And the other case is that here's the y-axis. Case 2 is that the vertex of this parabola is somewhere to the left of the y-axis. And we're restricting our attention to non-negative values of beta. So we're not, this negative value of beta that corresponds to this vertex is not in consideration. We're restricting our attention to non-negative values of beta. And looking at this graph, the best value of beta in this second situation is just beta equals 0, because when we look at non-negative values of beta, the smallest value that this quadratic function ever achieves happens here where beta is equal to 0. It happens when this quadratic function intersects the vertical axis. So what this means is that in order to find a minimizer of this quadratic function when we are restricting our attention to non-negative values of beta, what we can do is first just find the vertex of this parabola, and then let's look at the first coordinate of that vertex. If that value of beta corresponding to the vertex of this parabola, if it is positive or non-negative, then that means we're in this case and we're done. That value of beta is our minimizer. On the other hand, if the value of beta corresponding to this vertex, if that's a negative value of beta, that means we're looking at this picture. And in that case, the minimizer for our optimization problem is 0. In that case, the best choice of beta is 0 when we're restricting our attention to non-negative values of beta. So let's find the vertex of this parabola. Let's find the minimizer for this quadratic function. And we can find the minimizer for this quadratic function just by setting the derivative equal to 0. The derivative of this function of beta is 1 plus 1 over alpha times beta minus beta hat. And now that's the derivative of our quadratic function. Let's set this equal to 0, and now let's solve for beta. So if we multiply through by alpha, then we get alpha plus beta minus beta hat equals 0. And so that means that beta is equal to beta hat minus alpha. And as I mentioned, there are two possibilities here. Either case 1, this thing, beta hat minus alpha, is non-negative, and that means that the vertex of our parabola is to the right of the y-axis. That means that we're in this case here where the vertex of our parabola is to the right, and that means that this is simply our best choice of beta. That means that this is our solution to this optimization problem. And the other case is where beta hat minus alpha is negative, and that means that we are in this second case where the vertex of our parabola falls to the left of the y-axis. And in that case, the best choice of beta is just 0, because we're restricting our attention to non-negative values of beta. So let's put these pieces together. What we've discovered is that if beta star is the minimizer for this optimization problem that we want to solve, then what we've discovered is that beta star is equal to beta hat minus alpha if beta hat minus alpha is non-negative. In other words, if beta hat is greater than or equal to alpha, and beta star is equal to 0 otherwise. That's what we've discovered. In case 1, where beta hat is non-negative, this is a nice explicit formula for the proximal operator. This is the answer. And we can. Now what about case 2, where beta hat is negative? This is case 2. In this case, I claim that there is no point in considering positive values of beta. When we're solving this little optimization problem, I claim there's no point in considering positive values of beta. And let's try to understand why that's true. So let's draw this picture. Here's the origin. Here is beta hat, which is negative. I claim, and here's a candidate value of beta, which is positive. I claim that there's no way that this positive value of beta could be a minimizer for this objective function. And if we start with a candidate value of beta that's positive, we can improve beta just by moving it to the left a little bit. If we start with this beta value and move it to the left, then certainly this term gets smaller, but also this term gets smaller because beta is moving closer to beta hat, so this term gets smaller. So both terms get smaller. That means there's no way a positive value of beta could be optimal in case 2. And that means that we can restrict our attention to negative values of beta, or at least non-positive values of beta. So this is equal to the argmin, and we're going to restrict our attention to negative values of beta. And now, because we're restricting our attention to negative values of beta, this term, the absolute value of beta, can be replaced. That's just equal to minus beta. And then this term remains the same. So we have 1 over 2 alpha times beta minus beta hat squared. And that simplification, being able to remove this absolute value sign, is nice because, again, this function that we want to minimize is a quadratic function. It's a parabola that opens upwards, and we know how to minimize parabolas. And yes, it's a slight complication that we're restricting our attention to negative values of beta, but this problem should be fairly easy because we're basically just minimizing a quadratic function. So let's find the value of beta that minimizes this quadratic function. Setting the derivative equal to 0, we get minus 1 plus 1 over alpha times beta minus beta hat equals 0. Now let's multiply through by alpha. So we get minus alpha plus beta minus beta hat equals 0. And so that gives us beta equals beta hat plus alpha. And as before, there are 2 cases. If this value of beta is already negative, then we're done. We have found a minimizer for this optimization problem. If this value of beta is positive, then the best choice of beta to minimize this objective function when we're restricting attention to negative values of beta or non-positive values of beta, the best choice of beta in that case will just be 0. So putting those 2 pieces together, the best choice of beta, I'll call it beta star, the minimizer for this optimization problem is going to be either beta hat plus alpha if beta hat plus alpha is already negative. In other words, if beta hat is less than or equal to minus alpha, and otherwise the best choice of beta is just going to be 0 otherwise. This is a formula for the proximal operator of our function r in case 2 where beta hat is negative. So in summary, here's the answer that we got in case 1, and here's the answer that we got in case 2. And there's actually a nice visual way to understand these formulas. Let's draw a picture of the number line, and here's the origin, and here is beta hat, the input to the prox operator. What is this formula telling us visually. What this means is that starting at beta hat, we just move to the left towards the origin a distance alpha, and that is our new point. That's the answer. But this formula only applies if beta hat is greater than or equal to alpha. If beta hat is less than alpha, then when we move towards the origin, a distance alpha, we would actually cross over to the other side into negative territory. And that would be moving too far. What this zero is telling us is that as we move towards the origin, a distance alpha, if we hit the origin, then we should stop at the origin. So what this formula is telling us visually is start at beta hat, move a distance alpha towards the origin, but stop if you hit the origin. And this formula is telling us the same thing. And if beta hat is negative, it's telling us a similar thing. What this formula is telling us is starting at beta hat, we should move towards the origin a distance alpha, but if we hit the origin, then we should stop. So in both cases, there's one single visual interpretation that explains, that describes both cases. Start at beta hat, move towards the origin, a distance alpha. If you hit the origin, stop. That's the visual meaning of the proximal operator of the absolute value function. It's kind of like beta hat shrinks. Sometimes people call this the shrinkage operator because it's like beta hat is shrinking towards the origin. If you hit the origin, you stop. If you think about this visual interpretation of the proximal operator of the absolute value function, you can convince yourself that there's one simplified formula that handles both cases at the same time. And here's that simplified formula. This one formula for the proximal operator of the absolute value function handles both cases. This formula is true if beta hat is positive. It's also true if beta hat is negative. But I need to explain what I mean by clip. What is this clip function? This clip function takes a number beta hat as input and it just clips it. If beta hat is greater than alpha, then it gets clipped and the result is just alpha. So inputs that are larger than alpha get clipped down to alpha. Inputs that are less than minus alpha get clipped so that the result is just minus alpha. So everything that's outside of this range gets clipped. Everything out here gets clipped down to here. Everything out here gets clipped to here. Everything outside of this range gets clipped. It's the clip function. And if beta hat is already inside this range, then the clip function doesn't change anything. It does nothing. In that case, if beta hat is already inside this range, it doesn't need to get clipped. It's already in this range. So the clip function just returns beta hat as output. The clip function doesn't do anything in that case. So so I claim that this formula is just one single simple formula that always gives us the correct answer for the prox operator of the absolute value function. So let's think about what this formula is doing visually, and we can recognize that this formula is doing exactly the same thing that the proximal operator of the absolute value function does. So what happens if beta hat is greater than alpha? Then when we clip beta hat, we just get alpha. So this becomes beta hat minus alpha. And that's what we wanted. In that case, we're doing beta hat minus alpha. We're just moving towards the origin a distance alpha. Now, what if beta hat is in this range between 0 and alpha? Then clip of beta then the clip operator, the clip function does nothing. So we're just doing beta hat minus beta hat, which is just 0. And that also is the correct answer, because if beta hat is in this range, then what does the prox operator do? It shrinks all the way to the origin. So this gives us the same answer, the correct answer in that case. What happens if beta hat is over here in this range? Then the clip function, when beta hat gets clipped, the result is minus alpha. And so we're doing beta hat minus negative alpha. In other words, beta hat plus alpha. And that's exactly the correct thing. That agrees with our formula that we found. In other words, if beta hat is over here in this range, what this formula is telling us is that we just move to the right a distance alpha. And finally, if beta hat is in this range, then the clip operator does nothing. So in that case, we're doing beta hat minus beta hat, which is just 0. And that makes sense. So in summary, everything in this range here gets mapped to the origin. That's correct. That's what this function is telling us, and that agrees with what our proximal operator does. Everything that's out in this outer range just gets moved towards the origin at distance alpha. That's what this formula is telling us. So this formula, when it comes time to write Python code to implement this prox operator, this formula is a simple, easy way to do it. Now that we've figured out how to compute the proximal operator of the absolute value function, we're ready to compute the proximal operator of the L1 norm. So suppose that R of beta is equal to the L1 norm of beta. In other words, the sum of the absolute values of the components of beta. To evaluate the proximal operator of the L1 norm, we have to solve this optimization problem. We have to find the vector beta that minimizes this objective function. Here we have the L1 norm of beta. Here we have the square of the L2 norm of beta minus beta hat. This term discourages us from moving too far away from the input vector beta hat. There's something very nice about this objective function, which is that this objective function is a separable sum of the components of beta. If we expand these terms, if we write these terms out in more detail, we will see that what we get is a term that depends on beta 0 plus a term that depends only on beta 1 plus a term that depends only on beta 2, and so on. That's called a separable sum. Let's see this in detail. This term, that's equal to the absolute value of beta 0 plus the absolute value of beta 1 plus ... plus, finally, the absolute value of beta d, the final component of beta. And what about this term here? This is equal to 1 over 2 alpha times beta 0 minus beta 0 hat squared, and then plus 1 over 2 alpha times beta 1 minus beta 1 hat squared, plus ... and then finally plus 1 over 2 alpha times beta d minus beta d hat squared. So if you expand this term and you also expand this term, then you find that this objective function can be written in more detail as a sum of all these terms. But now let's look at how all these terms can be grouped in a certain way. Here we have this part depends only on beta 0. And then this part depends only on beta 1, and so on. And then this part depends only on beta d. So that's what I mean when I say that this objective function is a separable sum. It's a sum of a term that depends only on beta 0, and then another term that depends only on beta 1, and then finally a term that depends only on beta d. Remember, we're minimizing with respect to the components of beta. These numbers, beta 0 hat, beta 1 hat, beta d hat, the components of beta hat, those are fixed. Those are given. Those are not variables in our optimization problem. They're fixed and they're given in advance. The optimization variables, the variables that we can control and the variables we can change, are just the numbers beta 0, beta 1 through beta d. That's what we have control over. So this is a separable sum. How can we choose the numbers beta 0, beta 1 through beta d to make this big sum as small as possible in order to minimize this big sum? Well, what we should do is choose beta 0 to make this first term as small as possible. And we should choose beta 1 to make this second term as small as possible. And so on. We should choose beta d to make this final term as small as possible. And this first subproblem, where we choose beta 0 to make this first term as small as possible, that little subproblem is independent of these remaining problems. And this second subproblem, choosing beta 1 to minimize this term here, that's independent of how we chose beta 0. It's independent of how we chose all the other components of beta. What we have is a bunch of subproblems that can be solved independently. We have one subproblem for each component of beta. But let's look more closely at this first subproblem. We're minimizing this expression with respect to beta 0, the number beta 0. Here we have the absolute value of beta 0, and then here we have beta 0 minus beta 0 hat squared. Isn't this exactly just evaluating the proximal operator of the absolute value function? That's all it is. And we already figured out how to do that. To find the best choice of beta 0 that makes this first term as small as possible, all we have to do is take beta 0 hat, that number, and plug it into the proximal operator for the absolute value function. And what about this second subproblem, the second independent subproblem? Here we have the absolute value of beta 1, and here we have beta 1 minus beta 1 hat squared. Again, isn't this just computing the proximal operator of the absolute value function? And so we know how to do that. So the best choice of beta 1 is to find the best choice of beta 1, just take this number beta 1 hat and just plug it into the proximal operator for the absolute value function. And it works the same way for each of these subproblems. We already know how to solve each of these subproblems. That means we know how to solve this original problem, which is what we wanted to solve. And all we have to do is take our vector beta hat, take that vector, apply the proximal operator of the absolute value function to each component of beta hat, and that gives us the best vector beta. That gives us the answer. The vector beta that minimizes this objective function is the vector that you get by starting with beta hat and applying the prox operator of the absolute value function to each component. In other words, each component of beta hat is going to get shrunk towards the origin, a distance alpha. And if we hit the origin, then we stop. So now we know how to compute the proximal operator of the L1 norm, and ultimately it turns out to be pretty simple. We're given a vector beta hat as input. We shrink each component of beta hat towards the origin, a distance alpha, and that's it. That's the answer. That's all we do. There's one more detail we need to talk about before we're ready to implement this in Python. When we're doing linear regression and we're using L1 regularization, in other words, when we're solving a lasso problem, we typically do not include the first component of beta in the regularization term. This first component of beta, beta 0, is left free. So the regularization function that we use is defined like this. Here we have the sum of the absolute values of all of the components of beta except for beta 0. Beta 0 is left free. So we also need to know how to compute the proximal operator of this modified regularization term, which does not include beta 0. To evaluate the proximal operator of this modified regularization function, we have to solve this optimization problem. And here again, this objective function that we're minimizing, again, is a separable sum. So we can take a very similar approach. We can take the exact same approach. Let's write out this objective function in more detail. This term in detail is equal to 1 over 2 alpha times beta 0 minus beta 0 hat squared plus 1 over 2 alpha times beta 1 minus beta 1 hat squared plus dot 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 plus 1 over 2 alpha times beta d minus beta d hat squared. And let's write out r of beta in more detail. R of beta is equal to the absolute value of beta 1 plus dot 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 plus the absolute value of beta d. So this objective function, written out in more detail, is the sum of all these terms. And to minimize this objective function with respect to beta, we have to minimize the sum of all these terms. But once again, this is a separable sum. We have this first term. This first term depends only on beta 0. Notice there's no contribution coming from r of beta here because we're using our modified regularization term. This second term depends only on beta 1, and so on. This final term depends only on beta d. So this is a separable sum. How do we choose the components of beta to make this big separable sum as small as possible? Well, as before, we should choose beta 0 to make this first term as small as possible, and we should choose beta 1 to make this second term as small as possible, and so on. We should choose beta d to make this final term as small as possible. How do we choose beta 0 to make this first term as small as possible? Well, clearly the best choice of beta 0 is just to choose beta 0 equal to beta 0 hat. Then this first term is 0, and you can't do any better than that. How should we choose beta 1 to make this second term as small as possible? Well, here we're just evaluating, as before, we're evaluating the proximal operator of the absolute value function. So to find the best choice of beta 1, just take beta 1 hat and plug it into the proximal operator for the absolute value function, and so on for the remaining problems. To find the best choice of beta d, take beta d hat, plug it into the proximal operator for the absolute value function. The only difference is in this first term. The best choice of beta 0 is equal to beta 0 hat. So we have now figured out how to evaluate the proximal operator of this modified regularization function r. We're given a vector beta hat as input, and all we do is we apply the proximal operator of the absolute value function to each component of beta hat except the 0th component. The 0th component is left unchanged. In other words, we take the vector beta hat as input, we shrink all the components of beta hat towards the origin at distance alpha, except for the 0th component of beta hat, which is left unchanged. Now we're ready to write a Python function that evaluates the proximal operator of the L1 norm. So let's first import NumPy. And now the first thing I want to do is implement the clip function. So let's make a function called clip that's going to take as input beta. Beta could be a number or it could be an array. It could be a NumPy array. And the second input to our clip function is going to be alpha, which is a number. Now, the first thing we need to do here is the components of beta that are larger than alpha need to be clipped. So let's do clipped equals np.minimum of beta comma alpha. Okay. Now, the next thing that needs to happen is the components of beta that are less than minus alpha need to be clipped. So let's do clipped equals np.maximum of clipped comma minus alpha. And then let's return clipped. So here's our clip function. There it is. Let's test it out and make sure it's working. Let's set beta equal to 5 and alpha equal to 3, and let's print clip of beta comma alpha. And let's just make sure that we get the right answer. Okay, the answer is 3. That makes sense. Let's set beta equal to 2 and try it again. Okay, the result is 2. How about minus 5? Okay. Let's also test that this clip function works correctly when beta is an array. So I'm going to have beta just be a list of randomly generated numbers. It'll be a list of 20 randomly generated numbers. And alpha, I'm going to set equal to 0.5. And I'll do clipped equals clip of beta comma alpha. And now I want to plot the result. So let me import matplotlib.pyplot as PLT. And now here I'm going to do plt.plot of beta and also plt.plot of clipped. Let's take a look at this. Okay, So in blue, we see the original array of numbers, and in orange, we see the clipped version. So we can see, looking at this, values of beta that were larger than 0.5 have been clipped down to 0.5, and values of beta that were less than negative 0.5 have been clipped up to negative 0.5. All of the clipped values shown in orange are in between minus 0.5 and 0.5. That's what the clip function does. So now we're ready to write a function that evaluates the proximal operator of the L1 norm. So let's create a function called prox L1 norm. It's going to take as input a vector beta hat and also a number alpha. And the output of our function is just going to be beta hat minus clip of beta hat comma alpha. That's it. And then we just return this output. That's our function that evaluates the proximal operator of the L1 norm. This is just using the formula that we discovered earlier for the proximal operator of the L1 norm. Now there's one more little detail we need to be careful about. I mentioned that when we're solving a lasso problem, we typically don't include beta 0, the 0th component of beta, in the regularization term. And we need to allow for that possibility in this function. So let's have a third input, which is going to be just a flag, and it's going, let's call it penalize all, and the default value will be true. If this input flag, penalize all, is set to true, that means each component of the input vector beta hat, every single component is going to get shrunk towards the origin. But if penalize all is false, then the 0th component of the input is going to be untouched. All the remaining components will be shrunk towards the origin, but the 0th component is untouched. So let's put in an if statement, and we'll say, if not penalize all, then out of 0 equals beta hat of 0. So in this case, the 0th component of beta hat is untouched. Let's test this function that we've just written. Let's create an array of numbers that goes from minus pi to pi with a spacing of 0.01. And let's set beta hat equal to the sign of this list of numbers. So beta hat equals np.sign of x vals. And now let's apply the proximal operator of the L1 norm to beta hat. So let's do prox equals prox L1 norm of beta hat. I'll set alpha equal to 0.2, and we'll use the default value of penalize all, which is true. And now let's take a look at, let's plot beta hat like this. And let's plot also this variable prox that is the result of applying the proximal operator of the L1 norm to beta hat. So here I'll do x vals comma prox. And let's take a look at this. So here in blue, we can see the input vector beta hat, and in orange, we see the result of applying the proximal operator of the L1 norm to beta hat. And we can see here that each component of beta hat has been shrunk towards the origin. And you can see also that the ones that were already within a distance of 0.2 of the origin have been shrunk all the way to 0. So what we do is each component of beta hat just gets shrunk towards the origin. If you hit the origin, then you stop.